Heat transfer, we're looking at basics and some steady state heat transfer. It is arguably chapter 5, I should have called it rather. Let me just call it what it is. Chapter 5, what we're calling. Typically, I do heat transfer at the end, but I decided to leave air compressors at the end. And yeah, so I just thought I'll cover certain things which I've always been wanting to cover in proper detail. You know, you never get a chance to actually do it right, but hopefully I can do it justice. It's people using a different link. Oh, I see. Okay, okay. Yeah, so let's just give them a few minutes to join. Yeah. But when you pause, we have to start.
Yes, I just went to another link. I checked. Yeah, there are guys there.
Yeah, thanks. Thank you, Mr. Matoso. You're always very diligent. Thank you. Yeah, I did say, I did say, in the previous lecture, but anyway, obviously not everyone is. We'll just wait for them to join. Mr. Abreu, Mr. Doyle, or just chase those people to join the link, man.
Okay, so I was on the other link. Believe it or not, the reason I joined the morning class so late was because I was waiting in the other link for like 20 minutes.
Yeah, sorry about that. The larger could have been slight confusion, but I still see no one joining though. That's the thing. Hey, 15 people, 2 joining. Fantastic. It's another nice section. Yeah. We start to have some fun with it. I've posted the notes all on Blackboard. There is one thing I probably didn't post, which I got from another like source, university kind of shit. Not wow. Yeah. Anyway, some good problems there to solve. Yeah, we'll have a look at that. Fortunately, just found on the internet, and that's lucky for us. Okay, cool. Am I recording even? I am recording. Okay, I've been recording. Okay, so chapter 5, heat transfer, basics and steady state heat conduction. Yeah, let's have a go. So what they're saying here, we all know from experience that a cold can drink left in a room warms up and a warm can be left in a refrigerator cools down. All right. This is accomplished by the transfer of energy from a warm medium to a cold one. Obviously, we are aware of this. This is the second law of thermodynamics. And we always know that energy transfers going from a high temperature to a lower medium. Obviously, we've also, yeah, well, in a fridge it was obviously different. But anyway, and they say when the energy transfer stops when the two temperatures reach the same temperature. So, by the way, when I'm saying the same temperature, I think what I should say here is steady state, just as a implicitly mention that there, so just to suggest. And also, you recall that from thermodynamics, energy exists in various forms. Particularly in this text or this chapter, you're interested in heat, right? And this is a form of energy that is transferred from one system to another as a result of a temperature difference. So obviously, we're looking at heat transfer. So before we get there, just some analogies with heat. What is exactly heat? If we're talking voltage, right? If we want current to flow, we need a voltage difference. We want fluid to flow, we want a pressure difference. And if you want heat to flow, you need a temperature difference. And obviously, we're dealing with heat transfer, and this is what we're going to be looking at. So what they say here is that the heat transfer of energy as heat is always from a high temperature, a high medium to a low medium. And basically, it stops when they reach the same temperature, right? That will be called the steady state. Basically, and I don't know if you had some basics on heat transfer. I think some of you guys did. There's 3 different modes, and it's essentially conduction, convection, and radiation, right? And all modes of heat transfer require existence of a temperature difference, and all modes are from high to lower, right? And basically unpack each one. So what is conduction? So why don't I have something? So conduction basically is a heat transfer which basically takes place in solids, liquid. It can take place in all 3, right? However, it's predominantly solids. What they do say, it's a transfer of energy from a more energetic particle of a substance to a less adjacent particles. So I don't want to talk too much about the science, but basically it's the predominantly one happening in solids. So I want to just show you like in conduction. I was looking for an image. Yeah, okay. So I'll just copy the span over here, but yeah, that's a good one. I'm just looking for a nice idea of conduction. It's beyond me why I didn't actually have a picture, an image there. Kind of really bothering me anyway. Yeah, so as an example, just to suggest what's happening. You don't really need that picture. Hot side, cold side, same thing. Okay, cool. You know. Yeah. So what's basically important is to know that in gas and liquid, the conduction is basically due to collision and diffusion of the molecules due to random motion, which is not something you really require to know. Furthermore, in solids, it's more about the vibration of the molecules in the so-called lattice, in basically the way they arrange, and the energy is transported by free electrons. In terms of conduction, what is conduction if you want to think about it? As we're heating that pan over there, it's there's a temperature difference on the inside of the pan from the outside of the pan, and as the heat is traveling through the thickness of the actual pan, and that is called conduction. And you understand what conduction is? Basically, to model conduction, we use Fourier's law, And Fourier's law is K times A, change in delta over change in X. So what's obviously important is two things which you have to kind of be aware of conduction. You need, I'll talk about how it works, but K is the thermal conductivity, which we're going to obviously unpack. And the thermal conductivity, it depends, and that's a function of the material itself, and obviously the thickness. And obviously, when you say thickness, that's what I mean. There's some solid, or there's some solid that's actually where there's some thickness in between the heat. Just important to note. Obviously, we're going from hot side to cold side. That are the heat travels. The travels in this case from left to right. Furthermore, you have the thickness of the hole, right? So that is in direction. That's the heat travels parallel to the thickness. However, the area we use is the perpendicular area of that particular hole. So we'll unpack. That's just the idea of what conduction looks like in a three-dimensional thing. Again, X, thickness X, the normal area, obviously that's the perpendicular area, and yeah, that's basically just a way, and that's how so I'm just using a block as an example. So we need a hot side T1 and a cold side T2. Obviously you can swap those around, it doesn't really matter. And the heat travels through the thickness, and the area we use is the perpendicular thickness. So that is for conduction, right? That is particularly for solid. Here it's exactly the same thing. And I'll talk about the thermal resistance later on, but there is a concept of thermal resistance we actually include, which we'll be using a lot. Once again, it's prominent mostly in solids because it's the only one possible there. So solids mostly have conduction, right? The object we'll be looking at is also cylinders and spheres, probably mostly, the three objects. So it will be a rectangular shape or solid wall. You've got a cylinder, and you've got a sphere. So what are you basically seeing there? They're putting this R, is called the thermal resistance, which I'll unpack again. But basically, each object will have a different kind of thermal resistance, and that's on the virtue of its dimensions, geometrical property, and thermal conductivity. So then just talking about thermal conductivity, what is the difference? Basically, thermal conductivity of a material can be defined as the rate of heat transfer per unit thickness of a material per unit area per unit difference. So what it basically is, it's a measure of a material to basically conduct heat. So we have a higher K value, just showing on the two pictures there what conductivity is. We apply some heat. If you have a higher thermal conductivity, you can see the heat will travel faster, right? If you look at the so-called aluminum nitride, compared to that zirconia over there, it travels a lot slower. So, yeah, high value. One of the analogies I used last year, if you remember, if you look at a ceramic coffee mug compared to those camp mugs, which is made of, I'm not sure, it's not some steel, it's obviously some alloy. Obviously, if we throw hot water into those mugs, on the ceramic side, you don't feel much heat, right? Like your normal cup, your porcelain cup, I guess, maybe it's porcelain, that's the actual material. However, on that so-called alloy mug, there may be some cast iron or whatever, aluminium, you immediately feel the heat when you I don't know if you know what I mean. I don't know the prison mugs, if one could also use. Furthermore, a high material with a high thermal conductivity is called it's called a good heat conductor. It's a conductor, whereas one with a low material is called, or the poor heat conductor is called an insulator. So, insulator, if you look at a typical geyser blanket, obviously you've seen insulation, especially on board, where we typically don't want a lot of heat, normally on the hot side of in terms of refrigeration, on our discharge side, on any part where we don't want to lose heat, we typically insulate, and those materials have low thermal conductivities. Glass within the region of like there's urethane, which is like 0.026, and glass fiber, which is like glass, or you get polyurethane as well, which is essentially that the urethane I was talking about. So one, wherever higher one, I mean diamond, that's typically the highest at room temperature. It's like 2,300 watts per meter Kelvin per meter degree. Copper's also quite diamond's the best one at room temperature. So I'm just making you aware. And again, conductivity, just think of solids, that's predominantly the main one, and that's what thermal conductivity essentially is. So just recapping back to this, it's a material property. So obviously a different material have a different thermal conductivity. Here we have a schematic of different materials and different states of matter and how the thermal conductivity is. So if you notice, solids will have higher, like metal alloys, solids will have higher thermal conductivities. And they're saying non-metallic crystals such as diamond, graphite, solid silicon carbide, quartz, they have extremely high thermal conductivities. Imagine, I don't know what kind of device, but probably a heat exchanger, maybe we need higher thermal conductivities. We design the whole thing out of quartz. Obviously, manufacturing using quartz is like some kind of crystal. It's just unfeasible to manufacture. And as we drop along the scale there to the left, you know, those gases have very poor thermal conductivity. I mean, that's if you think about water. In particular, you're running heat through water. Obviously, it takes some time compared to a metal or a solid. So solid, it starts with solids higher, goes to liquids, and then eventually gases. Gases, there's barely no thermal conductivity. Not no, it's in smaller magnitudes, obviously, right? Okay. And again, the thermal conductivity really just as backdrop. It's in solids particularly. It's to do with the atomic structure of the solid itself, you know, and the amount of free electrons. Obviously, that goes down into physics with your different types of, depending on what it's made of, carbon. Carbon is so many electrons and so things like that. So nothing important for you to know. We're not looking at that as an engineer. Yeah, then again, this is just what's important to note, that thermal conductivity is also a function of temperature. You can think of thermal conductivity as a resistance, you know, like resistance within your electrical resistance. If you increase the temperature, we get higher resistance. And they're just showing a display value of, in fact, it's a decrease. And depending on the material, it will, sorry, it doesn't always increase. It's a function of temperature. I didn't say that. So if you look at copper, as we increase the temperature, our thermal conductivity drops. That is correct. Likewise with aluminium. However, they do say there are things called superconductors, and basically when we decrease to nearly absolute zero, there's essentially no more conductivity. They say, as an example, conductivity of copper reaches a maximum value of 20,000 watts per meter squared, which is essentially ridiculous. At 20K, it's 20 Kelvin, obviously, and which is about 50 times. So if we actually reduce our temperature to around absolute zero, which is what minus, what's absolute zero? Like how many Kelvin is that? Yeah. Well, metals particularly behave very funny, very funny. And you can see there's a few things one must be aware. But typically for our analysis, we assume a thermal conductivity to remain constant for the ease of calculations. Okay, so we move on to the next. What's the next? What is this? The next mode of heat transfer. We start with convection. And in convection, what convection is basically, I'm just going to go, you'll get to the nice part, but the layman is, just imagine a hot egg, and if you're blowing air over it, when you have a solid and a liquid, and a liquid is basically, obviously a gas, maybe it's flowing over the actual object, we have some kind of convection. So what is this convection, right? So here they give an example, and they say, okay, yeah, so convection is a mode of energy heat transfer between a solid phase and adjacent liquid or gas that is in motion. So over there, I've got some object which is fixed to the ground. I'm not sure exactly what's providing the heat. And what we're seeing is air traveling over the object. This is obviously done through finite element analysis. And it's essentially cooling this object. I don't know how the air is based. You see like it's flowing downwards. So that air flowing over this particular object, which is cooling it, that is called convection. Obviously, this can be a liquid as well. What's important to note is, I'll say I'll also say it again. So it's an energy transfer between solid surface and adjacent liquid or gas that is in motion, and it involves combined effects of conduction and fluid motion. So when you think of convection, always think of fluids rather. That is our eye when we think about it. That's where you're typically going to see it. What's important to note, the saying the faster the fluid motion, obviously, the greater the convection. And so in the absence of any bulk fluid motion, the heat transfer between a solid surface and an adjacent surface by pure conduction. So if there's like stagnant air, right, let's say it's not moving, then basically the air is transferring heat through conduction. However, if it starts over a certain velocity threshold, what we tend to find is that we have a bit of more, it's called convection. Yeah, this is what I actually want to talk about in that slide. Again, let's say here an example of convection. There's just more examples. As you can see, air traveling over this particular fins over there. Let's say consider cooling of a hot block by blowing air over the top surface. So you have a hot block, maybe you put it in the furnace, maybe you heat treated something, and as you maybe blow air over it to cool it, they're saying the energy is first transferred to the layer adjacent to the block by conduction. However, the edge is carried away from the surface by convection. So yeah, so as you can see, it's like I said, what they're showing there is the variation of velocity over the thing, and they're basically saying the faster it goes, that's when it goes from conduction to convection. And they basically say that this is the combined effects of conduction within the air that is due to the random motion of air molecules or the bulk or macroscopic motion of the air that removes the heated air near the surface and replaces it by cooler air. Right. So essentially what convection also is, or I'll talk about the natural convection, is that you should know that hot air rises, and basically that temperature difference of of hot air was rising to the top and cold at the bottom provides some kind of flow over whatever object. Very important. This is again and this is convection can furthermore be bifurcated into two things. One is forced convection, and what forced convection is when fluid is forced to flow over surface by external means. And this is examples of fan, pump, or wind. So that is what forced convection is. Then in contrast, which I was talking about, is natural or free convection. Like basically as I'm sitting in the office here, as I sit in the office, and by the virtue of me being in air, and the air has different temperatures all around. Obviously, some is heated through the window. There's some air traveling, and this is basically caused by the buoyancy forces that are induced by density difference, basically the variation of temperature of fluid. However, if I put my aircon on, clip my aircon on, put it on, at the back there's a fan, and obviously what the aircon does is extract energy from the inside here and inject it to the back. However, there's also fan to facilitate the movement of air, and that is basically forced convection. An example is if you roll down your windows in your car, that is like natural convection, and maybe arguably as you put your aircon on, that is kind of like a forced convection thing. Obviously, it's kind of debatable. Yeah, there was an example obviously of the hot block, which was basically the main thing. Another important thing to note is that the heat transfer process that involve phase change of fluid is also considered to be convection, because the fluid motion induced during the process, such as the rise of vapor bubbles during boiling or the fall of liquid drops during condensation. So what I mean there, if you look at a refrigeration particular example, in the evaporator, there's a phase change from liquid to vapor. That is also titled convection. And whereas in the evaporator we are taking liquid and we're evaporating, that is also called convection. Typically we call it latent. There's latent energy. Heat can also be classified as latent and sensible, but I'm just making aware. So for us to model the process, we use Newton's law of cooling, which is Q equals H area times the temperature difference. The key thing is you're always going to find a temperature difference. So if you look at convection, you have QHA times temperature difference, hot to cold, obviously from the surface to the environment. It's similar. It's very analogous to this formula over here. Ka, the change in temperature over the thickness, where K would be Ka is basically that H, and I'll talk about what that H exactly is. So here's an example. Again, I did mention the difference between natural and forced convection. Yeah, and then this is again the model. So H is called the convection heat transfer coefficient. You might be asking, where do you get that from? Because remember, with K, the thermal conductivity, obviously that's a physical property, and one can actually measure that. So each material has its own physical property, so you have to go in a lab and measure it. But with H, it's a bit tricky. And H, what is H? It's called the convection heat transfer coefficient, as I said, and it's not a property of a fluid. However, it is an experimentally determined parameter which value depends on a few variables, such as the nature of the fluid motion, how is it moving, the properties of the fluid itself, the surface geometry, and the velocity of the fluid itself. So just as an example, what convection coefficients can we expect? So we're looking at free convection. This is like natural convection, basically like in the top, like air itself now, where as I'm in the office right now, we have from around 2 to 2.5. That's a acceptable range for natural convection. That's of gases. Of liquids, in a case like that, is maybe me taking a hot marble, or I don't know why I'm thinking of a marble, and placing it into water maybe. And of course, a marble dissipates heat through the liquid. The convection coefficients, depending on the other factors, will range from 10, typically from 10 to 1,000. We're looking at forced convection. A case of that would be maybe a fan, maybe you have air. You find the forced convection will be 25 to 50 versus liquids. That's in the case of a pump. Maybe we're pumping thing, or having a heat exchanger, we're pumping liquid through tubes, maybe in excess of 50 to 20,000. And like I mentioned, in the things with the highest convection coefficient are when you have phase changes, and then it's due to boiling condensation. I'm making you aware there is a sister book which is called Heat Transfer, which we're actually using by Chengel and Gacha. And for each of those things, we can do analysis for. But we are solely focused on, in this particular level, is solely conduction. So steady state heat conduction. We do have elements of convection, but I mean, in heat transfer, you can calculate all the heat transfer coefficients of all of these things over here. There's a whole book on that, which, yeah, I'm just letting you know. That's a subject called heat transfer where you learn all of this, but we only focus on conduction. All right, we're getting close to where we need to be. Again, radiation. What is radiation? And essentially, just we don't typically unpack radiation that much. We don't really use it a lot, but basically, that's just heat transferred by electromagnetic radiation, and we particularly focus on thermal radiation. And just to note, all bodies basically emit thermal radiation. And I think I had an image of this dog. This dog, obviously, within itself, our blood and our heart pumping, that red you see over there is essentially it radiating heat. And for us to model that, we use that formula over there. Lord Kelvin, I think, developed this formula for him. And it's radiation is equal to emissivity. Sigma, which is the Stefan Boltzmann constant, the area again, and then T4 minus T to the power 4 surroundings. That T there must be in Kelvin. I've used this in my master's thesis. In fact, my master's thesis is also based on heat transfer and thermodynamics. And yeah, so that is how you model radiations. Obviously, you can see there's 3 different formulas, and obviously we can model all 3 radiations for any particular problem. What is more important here, they talk about something called absorptivity. There are properties, more properties called absorptivity, transmittivity, and emissivity of radiation. And what it typically is, just for noting, is that as you get radiation in the body, what tends to happen is that some of the radiation gets absorbed. That's basically to do with absorptivity. Some of it gets transmitted. We have something called transmittivity, and obviously have emissivity, which tells you how much of the actual radiation is going to radiate back. And there are some typical values of it. So this is more for noting. I don't think there's no real analysis on radiation. Obviously, in heat transfer, if you unpack it properly, you'll sort it out. And then finally, just to summarize, all in all, I'm saying in reality, heat transfer is always a combination of all 3. So basically, most of the time in real life, all these things are happening at the same time. And also, what's important to note that not all of them. So one could be, for instance, in a typical situation where maybe you have a cup. Maybe in such a situation, conduction is the predominant factor versus convection versus radiation. And radiation is typically the smaller one. And obviously, this is depending on where you are. And then over here, just a demonstration of how you basically add the stuff algebraically. So depending on what coefficient heat transfers you have, you're able to you just have to add them up algebraically. Like Q total be Q convection by Q radiation. But what it is talking about here is that they typically add the convection radiation component, and they combine it into one heat transfer coefficient H over there. So you'll see as you unpack. And this was actually an example, which I don't know why this is here, but this is the example what I was talking about in terms of radiation, where again we get some get absorbed, some gets emitted basically. And I should change the slide. And here's that same another saying: radiation is usually insignificant relative to conduction or natural convection, but negligible relative to forced convection. So they're saying thus radiation in forced convection application is usually discarded. So radiation is not something. It's only big in heavy temperatures. I'm talking about 700,000 degrees. That's where it becomes very predominant. But in the normal typical realm, we normally ignore radiation within our analysis. And that is just a small schematic of what's happening in summary, where we have conduction, there's two solids, convection, we've got a fluid traveling over there, and radiation being radiated. It's showing arrows pointing outwards. Yeah. So is there any questions just on the basics of heat transfer? What link am I using? Oh man, I'm using the refrigeration link, I realized. Ugh. Anyway, yeah. Okay, is there any questions with heat transfer? Any things you wanna maybe unpack? You confused with heat transfer? Yeah. Mr. Doyle, Mr. Matoso, Mr. Bali, Mr. Pereira, Ernest, Mr. Hermanus. Can I move on? Just give me a few thumbs up there in these. Thank you, Brent. That is just some backdrop, you know. Yeah, thanks, Mr. Bailey as well. Okay, so let's start going to the formal analysis and see where we're gonna go. Right. So first example. Okay, so what I'm gonna do here, I'm gonna throw it out here, and then I want to copy this formula for you, and I want to see you and try to solve this. So the calculations are fairly easy. Well, these ones anyway. This is a basic example. So I'm gonna give you 5 minutes to work this out. Right. So what we just want is the heat right through this wall. So we're going to start with this example. I'm going to talk about thermal resistance, what it is, and then we're going to start doing stuff like 1 hole, 2 holes, and then 3 holes, and maybe 4, 5 holes, and things like that. And we're going to be doing composite holes, and composite cylinders, and maybe composite spheres as well. So I'm making you very aware. Again, I'm just going to recap on that. I'm going to show you before you do. These are the things you need to know. So that one, right, and this over here. The 3 objects which will be assessed on. What's going to be interesting as well, after the next example, I'll show you what you're going to be doing, what you can actually check. But for now, I want you guys, I'm going to give you guys 5 minutes to try and solve this particular problem. So I'm just going to drop it there. Again, area is perpendicular, the area normal, the thickness as is, and you obviously use your SI units for this. Yeah, so the outer surface is a 5, it's a 5 by 6. This should be 5 by 6. Recall, they give you the thermal conductivity, and yeah. So let me just give you a see if you're sharp and you can do it. So I'll just give you a few minutes. Thank you. Are you guys done already? And please check all the information I've posted on heat transfer. Fantastic, Mr. Romanus. Yep. Yes, should be fairly easy to compute. I'll just duplicate the slide here. Yeah, should be easy to get. And all what you really have to do is Q. What is K? K was 0.69. What is my area? Let me just do this. Sorry, just forgive me. My area will be 5 times 6, so we have to use our area, this area over here. Right? That's 5 times 6. Then we need to add our temperature difference, which is 20 minus 5, and our thermal conductivity of 0.69. If you've done that, you should get 1035 watts. So that's basically 1 kilowatt of heat being transferred through that temperature difference. So you have to be very, especially if you're designing certain things, you see how much heat it's essentially traveled. Look at the thermal conductivity. A whole kilowatt is lost. Right, and that is why we really insulate a lot of things. Okay, so based on that, what we start doing now is I'll explain the concept of thermal resistance. Is for us to make our analysis more easy, especially when we're doing complex, complex things, right? So what's X is not 0.3, I'll sort it out now. Where is now? X is not 0.3. Oh, my bad. Yes, so this should be not 0.69, it's going to be 0.3. Yep, that's the thickness of the door. Yeah, thank you. Just want to cut this. Where are we? Yeah, so concept of thermal resistance. So what we just basically do is we take Fourier's law, and we basically take out the thickness. We take Ka over this, we take it out, and we are left with this, and then we take this and we just call it, I guess maybe I'm gonna call it R wall here, right? Now obviously you've seen them divided, but the reason is I think when I come to when I talk about I don't know if it's shown here, but basically it's going to be just 1 over that. Nevertheless, so then we just basically take out this and call that, so we call that the thermal resistance. So we just take out all the physical case properties of the material. What they say there, yeah, so that is for the one. What they're also saying there, it's analogous to resistance, where V equals I times R, and they're showing there's a voltage difference, and then RE will be your resistance, and then that's how your current flows. So, but what you have to just be aware of, it kind of swaps over, and I think I missed something within my actual lecture. Also, they just what they're showing is that we can represent the resistance as within a circuit, and you'll see what I mean. Yeah, basically, yeah. And then exactly with convection, we can do exactly the same. Where we use Q convection, H over this, HA, and we do a similar setup where we just take that out, and then we end up with one. Your thermal resistance for convection is 1 over HA, right? Similarly with radiation, we do exactly the same thing, and then we just take out E emissivity, or that's epsilon, and your sigma and your A, and then we have H rad. Also, yeah, and then you take E and A, and then basically have 1 over HA. You'll see it as we go along. And typically what they do is that they group your convection and radiation coefficient. Because, and they're saying in this way, all the complications associated with radiation are avoided. So just, yeah, in a nutshell, they combine the radiation and convection into one coefficient, and that's the typical things we look at. So yes, this is what I was talking about. So now, what we actually start doing, and what we look at is where we go into is looking at the temperature interfaces at various points across the actual hall. That is where we're actually going. And what you are seeing here is, let's say the heat is traveling this way, so that's 20 degrees, and so that's 10 degrees. We have to have a thermal resistance for different elements. So here, as you can see, this is the thermal. So outside, obviously, there's air. So we have convection over here. Then we have the thermal resistance to the wall, which is conduction. And then we have also on the other side, it's obviously the convection coefficient. So let's say there's 20 degrees outside and 10 degrees inside, and then the heat is obviously traveling this way. And then for each heat transfer, we have the so-called thermal resistances. As you can see, they are convection 1 plus Hall plus R convection 2. Similar to if you have like a voltage, like a voltage between 2 points. Do you guys get the concept of the analogy? Does it make sense to everyone? Can you just get a few thumbs up just to understand it's the same as a. Let me just make this bigger, sorry. That it's the same as, yeah, thank you, Mr. Doyle. Yeah, and Mr. Lemans. It's the same basically, Mr. Kiefer. So there, just basically them inputting the equation where it's 1 over HA, L or X over Ka. They're showing here basically two walls next to each other, and we basically what we're aiming to do at the end of it. What we typically do is find the heat transfer going across the whole Q, and then once we have Q, we're assuming the heat transfer rate is constant, and therefore we can find it at individual points. Obviously at individual points of the thing. Then in total, all we can say is U over A over R total. And obviously because the area is all the same, and yeah, we can do a quicker thing. Okay, yeah, so this is our first example. And what we will be doing is using this so-called thermal resistant approach. So if you go to your note, and I call the chapter, I called it chap 3. If you want to follow along with me, I think that is the first example. And what I'm going to do is basically, obviously, we had an idea of conduction through a wall. Just kind of focus on it. But now we're going to use our newfound knowledge with thermal resistance. So what we first do is typically work out. So I'm going to write Q. Just now remember, Q equals your temperature difference, right, divided by your R, right, your R total. Okay. So in this case, they don't provide us any convection, but they're saying that on a certain the temperature of the inner and outer surface of 16 and 2 degrees, they want the heat rate lost through the wall. So we need to find our thermal resistance for our conduction, and that is going to be L, which is that over Ka. And once we have that, we simply can say Q equals the temperature difference, which is going to be 16 minus 2, always high to low, divided by this R total. So remember, within your R total, you have L or X over Ka. So in this case, this is going to be 0.3. Remember, that's a thickness. We need K, 0.9, and we need our area. And our area is 5 times 0.3. No, 5 times 3. Right? Remember, it's always the perpendicular area, which is that over there. So now we're going to find our thermal resistance of this particular wall. Can someone just give me that value? I'll just move it up here. I should move it up there. I'll just have it here. And obviously you can find the heat immediately through that. 0.022 is good enough for me. So we're just boarding up concepts so you get comfortable. 0.022. The unit for this is, what is the unit for this? The unit is degrees per watts, Kelvin per watts. Where's my thing here? So the 0.022 degrees per watts, right? Once you have that, you can just simply chuck this guy in here, 0.022, and you can find your heat transfer through the day. So that's your first example. This one's minus probably done already. And you almost said, keep further start around, fantastic, 630 watts. I think that answer is correct. Yeah. Again, just for concept's sake, right? So that you know what I'm doing here. Okay. Obviously, I trimmed all the fat and came straight to the point of where I want to be. Next question, right? So it's the same thing. But now, what we're going to do, we have convection on both sides, right? And what do they want? So they determine the steady rate of heat transfer through this glass window and the temperature of its inner surface for a day, which room is maintained at 20 degrees while the temperature of the outdoor is minus 10 degrees. And they're giving you all the heat transfer coefficients, H1 and H2, and if you read this, says which includes the effects of radiation. So yeah, you won't be requested to find that. It's L, and yes, same thing. X equals L. So, a question like this, I think I'm gonna need my whiteboard here for this one. We're gonna have to write a bit. So we are holding it up to a test level will be. So I've posted a lot of things there. I'm gonna just post one more thing for you. And then you'll be sorted for heat transfer. So remember, I want you to focus on the composite walls, and I want you to focus on cylinders, and I want you to focus on spheres. Okay, so let's just quickly share this. Yeah, this could be our second last example for the day. Well, this could be our last one for the day. Because we will have a half lecture on heat transfer next week, and then we'll start on air compressors. Yeah, then probably 2 more air compressors, and then probably end off with probably end off with EPT if I get there, or maybe I'll just push more on air compressors, but we'll see. Cool. So over here, what we do typically for something like this, obviously you have your sketch. What? Yes. What they say, they want to know T1, right? This is on the inner surface. And we're going to work on outer surface, right? So this is outside. This is no. Where are we here? Let me just quickly see. Are we inside the house or? Okay, this is we are here, right? And extremely cold, and the heat is basically traveling out of our window here. Okay, so let's quickly see. So first thing is first, you normally start with a high temperature. So I'll call this T2, and that's 20 degrees. You can write it like this if you want. We're going to have our first resistance, which is in the convection. So we say R1 or R inner for internal convection. Then we have R glass. I'm making a circuit here basically, guys. And we have R outside. And then we have at the end T1, which is minus 10. I don't know how I should have it. It's before and after. You can change your temperatures on the way you want it, basically. So R inner, that's due to convection, conduction, and this is conduction as well, or convection as well. Sorry. So we start the problem. We find our thermal resistances of each part. So the first one is for convection. If you look at remember the formula, it's 1 over HA. So H1 is on the outside. So we can find that that's 1 over 10 times 0.8 times 1.5, right? What is our thickness for? Our thickness is 8 mil. Yeah, okay. So Silas, can I have that quickly? Very nice section. One of my favorite sections of all time. 0.0833 degrees per Celsius. 0.0833 degrees per Celsius. Oh, degrees per what? Degrees per Celsius. Are we happy with that? Where are we? Yeah, good. Next is conduction now. So I say R rho, and that's L. Silas wants X over Ka, same thing. Obviously, these properties are given to you. So X is 8 mol over what is this thing called again? Area. Oh, that's 0.78. Thermal conductivity of the whole at times 0.8 times 1.5. We could have worked on the area first. They plugged it in. Blah blah blah. Yeah, it's different ways to actually do that. Mr. Mutao, are you winning there? So don't forget that unit, guys. So what's it? 0.8. 0.0. What's it? 0.0. What's it? 0. Yeah, it should be 0.008547. Yeah. That is correct. Yeah, it's 8 millimeters. 0.008547. I think degrees per watt. Yeah, degrees per watt. Fantastic. Then we go into the outside, or what's this called? Or outside. Oh, yeah, as I have it. It's also 1 over HA. 1 over coefficients always given 40. Like I said, these coefficients and thermal conductivities are always given. So 0.8 times 1.5. And I'm not sure which value you get there. I think you should get an answer of 0.02083. Yeah. 0.02083 degrees per watts. Okay. Okay, cool. So once we have that, remember where we end off is our heat, is the temperature difference divided by our R total, right? So what I typically do here, I give a mark here, 1, 2, 1, 2, 1, 2, and now we have to find our R total, right? What is our R total? So R total, we simply add them up algebraically to get a total value. And remember, heat is traveling from the hot 20 minus 10 over R total. So what is my R total? Okay. 0.112, yeah. 0.11268. So obviously for that you get 2 marks here. Again also. Just for that, 1 mark or 2 marks depending. And if you work out how much heat is how much heat is traveled through the window, you should get an answer of around 200. Are you sure about that answer? Whoa. What's yeah, you should get 266, yeah. Into 4. Beautiful. 266.4. Gain 2 marks here. So like 1, so they like 10 marks. Mr. Manas, how do you enjoy that one?
So
Yeah. Great. So are we all happy with this one? Can I get a few thumbs up? Mr. Bali, Mr. Pereira, Ernest, are you following this? Before we do the last part. Okay, great. So what we do next, guys, again, not this, everything from here, it's not that air compressors can be a bit tricky for some people, but then there's 2 sections now, it's coming in the final. Okay, so what we need to do is find the temperatures, right? So how do we go about doing that? Okay, so what we do, let me just show you my approach quickly. So once you have the total heat transfer, all we do is we start at the temperature on the outside. So I'm going to call it, okay, just bear with me here, right? So I'm going to call this guy, I'm going to call this T0, right? Are you happy with that? T0. And then we're going to find T1, right? We're going to find T2, and we're going to call this T3. I think, so T is on the outside here, T0, I could call it T1, but I'm just following that train of thought here. So to find the temperature at each place, we're going to say, obviously we know that it's decreasing, we say T0, sorry, T1 is equal to T0 minus Q over the respective heat transfer coefficient at a particular place. In this case, for us to find T1, we know that there's convection, right? That's T1, that's on the surface of the window. So that is Ri. So we know it starts at 20 degrees, and now we're going to have to say 266.4 over the convection coefficient, or in this case, it's obviously a convection of the heat transfer coefficient at that particular point. So in this case, it's going to be, we found that thermal resistance was 0.0833, I think. So 0.0833. So let me just get that T1. Man, it's quick. As you can see there, it's minus 2.172. So that's how much heat was lost, minus 2.172. Is it 2.1? Sorry. Right, that's on the surface of the window. That's how cold on the surface of that window is, right? And you might think, yo, doesn't even make sense. What you're going to see is we're going to start at T0 and we're going to end up actually getting that -10 or close to the -10 value. So we do the same thing. So now for us to find T2, we take T1. So -2,1217 minus 266.4 divided by the conduction, was obviously that's going through conduction now, so it's R whole. So that's 0.00855, 0.08547. And then we get that answer. So we know that T2 should be less than -10 degrees, obviously. And if you do that, minus 4.45. So on the outside of the wall, what you actually feel is minus 4.45 degrees. For us to find T3, which is minus 4.45 minus 266, the heat remains constant, and then divide by the last coefficient, which is 0.02083. What answer do we get? What's that answer? There's no one saying anything there, 0.02083. Hey, is my conversion, my coefficient right there? What's my coefficient there? I'm getting a wait. What's the answer for that one? Looks bad. What's going on? Let me just see here.
Yeah, so I'm getting
So
a
your
massive
problem
number.
is you said Q over R.
Hey,
So it's Q times R. It's not Q over R, it's Q times R.
yeah, well, yeah, it's right. This is what I figured out just now. Yeah, it's Q times R. Yeah, it's Q times R. Yeah. So that's a mistake I've been making, I think. So if you do that again, sorry guys, my apologies. I got excited. So it's 20 times 0.080. I got too excited. 0.833 times 266. What do I get here? Yeah, nah, sorry about that. Minus 9.99. Okay. Oh, is the last one minus 9.99? I'm talking about you have to kind of recalculate all of this now in here. I got too excited.
But I think Jason's been giving you the correct answers for these other ones.
Oh, the other ones. It's all right, basically. Oh, I see.
I think. I don't know.
Yeah, it should be, because obviously it's following. It has to follow through. Yeah.
So
And that's I was calculating it. Yeah. So I said T0, T1 is going to be equal to T0. It should be minus Q times Ri. And that was the 20 minus the 266.4 times, yeah, there we go. That's about better. It's not divide, man. Times 0.083. So 0.0833. Obviously, you should get that answer. So anyway, welcome to S4. And obviously it's proven you've got 9.99, which is essentially exactly the same as the 10 degrees there. Jason has been giving the right answers. Otherwise, it wouldn't be making sense. 19, it's 219 something. Yeah, you got 217. I don't know. Yeah, 2171. Yeah, okay. So sorry guys, sorry about that. My bad. So you take T1. So it's going to be now. So the T2 over T1 minus Q times R whole. You take T3 minus T2 minus Q times R outside, and obviously you should get, and then you say T4. Yeah, then you should get T3, sorry. Yeah, that's the last one. T3 is the outside one, yeah. So you should get 9,99 here. Mr. Romanus, how was that? If you can do that, you're on your way to distinction. Minus 4.45, yeah. Okay, guys, any questions? We're at the end of the day. Oh, yes, mark allocations. 2, 2, and 2. Now, you probably don't get 2 marks for the spot, but it's probably just like 1, 2, 3, 4. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And 14 marks, yeah. For a typical question like this. Obviously, we're gonna expand upon this. Yeah, fantastic. Okay, guys, thank you for attending today. I appreciate it, for engaging. Thank you for your energy. And I will see you next week for thermals, where we will close off heat transfer. If you can work ahead, great. But next week we're gonna have 2 holes and then 3 holes, and then maybe a bit more. Now 2 holes, then 3 holes, and then I'll do a spherical example. Now a cylinder example, maybe cylinder example, and I'll do a sphere example. And then we'll be done with heat transfer. Then you'll start on air compressors, where we'll start on no clearance, single stage compressors, and yeah. I'm not sure if I'll be doing double or triple stages. I'm still deciding. And then I'll end off with hopefully engine and performance and testing. But all the next sections are small sections. They're not difficult to do. Obviously, you watch the lectures, you find the flow of what's happening. You should be more than adequate. But you must be able to do a 3 or to 4 problem. You'll see on the stuff that I post. Yeah, what you can roughly expect. But anyway, guys, thank you. Enjoy your weekend. Enjoy your Friday. Relax. We had a rough week. And then I'll see you again on Monday for, obviously, for strengths and electrodes. Okay, cheers, guys.